Buenos días a todos. Vamos a dar inicio en el seminario de Quantum Spain. El día de hoy tenemos a nuestra invitada, que es Miriam Lucio. Ella es egresada de la USC, del doctorado, y bueno, tiene desde su doctorado que está participando en el experimento LHCb. Y bueno, ella ha trabajado en la Universidad de NISQ en Ámsterdam como postdoctorado. Es especialista en física, en la búsqueda de nueva física, y actualmente es investigadora en la Universidad de Maastricht, aquí en Países Bajos. Y bueno, nos va a hablar el día de hoy de la computación cuántica en altas energías. Bienvenida.
Sí, gracias. Bueno, gracias por tenerme aquí. Si no os importa, voy a dar la presentación en inglés, pero preguntas me valen en cualquier lengua, menos el holandés. El holandés no, por favor, porque no lo controlo lo suficiente. Okay, so yeah, I'm going to talk about quantum computing applications in high energy physics, because that's the main focus of my postdoc in Maastricht, and that's where we are building our group. So a tiny introduction to why particle physics is a very challenging line of research. I'm sure you all have heard, but a refresher. We have this standard model in particle physics that has been so far a very successful theory. May I say, too successful for what we would have liked. So it basically describes the interactions amongst all the particles that we have in the standard model. But it has a lot of caveats, things that it fails to explain. So it becomes apparent that we need something else apart from the standard model. So for example, we don't have an explanation for the masses of the neutrinos or the dark matter and dark energy and so on and so forth. So yeah, it's basically our goal is to find some new physics that adds or replaces the standard model, and that's the main focus behind high energy physics. So before I continue this talk, I wanted to make a few points. Of course, this is far from a comprehensive list of lines of research going on in quantum computing for high energy physics, because that's a really wide topic, and there are many groups working on that. As you saw in my very first slide, I'm from an experiment which is located at CERN. So I'm going to be talking more about things that happen at LHC and LHCb, even though some things are common to other experiments as well, and I will briefly mention those. But yeah, please forgive me if I have unwillingly taken out one of your favorite results in this topic. And yeah, at the very first slide, I said it could be thought as a match made in heaven, quantum computing and high energy physics, because the events that we want to study in high energy physics are basically, well, they are quantum in nature. And actually, most of our observables come from interference effects or something that happens and has to do with quantum mechanics. So one could think that's like the perfect match, right? Because you have quantum computing, that's quantum in nature. You have high energy physics, also quantum properties. So it is true that this is the case, but even though the events in high energy physics are quantum in nature, the measurements are classical. And the explanation is very simple. It's because we cannot do it another way yet. So basically, we end up with electric signals in our detectors, and this is classical. So even though there's quantum underneath, there are some things that can be done more from the theory side or phenomenological side of high energy physics. I'm going to be discussing things that are more related to classical data, and you will see that that, of course, comes with all the disadvantages that you're all very well aware of. Now, there are some people that are looking into how to avoid this, how to avoid collapsing the wave functions and having the quantum data straight from the source into the quantum algorithm, which of course will come up with huge advantages and large speedups. But I would say, well, this is a bit beyond my expertise, but I it's something that most of the people working on this don't assume in our projects. And then, because my background is the LHCb, I'm going to introduce it because I personally think it's a beautiful detector. So for those of you who don't know it, the LHCb detector is one of the 4 main experiments at the Large Hadron Collider at CERN, at the border between France and Switzerland. So you have here the Large Hadron Collider, which is a circular collider, and it has 4 collision points, one of which is LHCb, which is this one. So it doesn't matter too much for the purpose of this talk, but basically it started as an experiment devoted to the study of a very particular type of decays involving big quarks, beauty quarks, and now it's basically a general purpose spectrometer. So we can consider this a general purpose spectrometer in the forward region. And then I also include this display of the LHCb detector. The details of the precision and so on, they don't really matter, but what does matter is that the collision happens here, where 2 protons traveling opposite directions collide, and then you have a bunch of particles produced, a huge number of particles produced, flying in the forward direction. And this matters because I'm going to talk about track construction a lot, and opposed to what would happen in another experiment at Atlas or CMS, which have more like an onion-like structure and the tracks go in 4π, this is only forward. So we have like layers of subdetectors that take care of recording the energy deposits and the hits. And the hits are the things that are going to matter the most for track reconstruction. But yeah, forward detector and several layers, actually a large number of layers. This is the first part of the detector, which we call the vertex locator. These are the proudest part of LHCb's detector. And basically here, there's no magnetic field. So the tracks that we would want to reconstruct will be mostly straight because they don't bend. And then they bend. So how does an event look like? You have here the underground experiment. When that data taking started, this person was not in the cavern. And this is what happens. So it's like parity transform, but you see here the event, and all these lines are all the tracks. This is a very, very messy event. And I'm not even showing you the events that are currently being measured with this data taking period, because we have just started. But this is from the old days where we had much, much less data. So you can see we have a lot of tracks flying through the detector that we need to reconstruct, and we don't have infinite resources. We don't have a lot of bandwidth. So we need to reconstruct events in what we call real time. Real time is a bit like, it's not exactly real time, but real time enough that we are scared about the future, because you have to reconstruct them fast enough that you know which things you want to keep and which you don't want to keep. So which things look more interesting to what you're searching for. But also, you know, you don't want to throw away a lot of things that would be useful for your studies. And actually, we need to, the rate at which we have to do this is 40 megahertz. So this is really, really a challenge. Actually, now we are fine because we have moved from CPUs to GPUs, and that's how we do it. But even GPUs will not be able to cope with this in the future. So to give you a time scale on what timeline we are talking about. Well, we are here. We have started taking data. GPUs are handling the data taking, so we are fine. And then we are moving towards the future, and the amount of data that is taken is going to multiply by about 5 times. So yeah, we need something else. GPUs will not do it, CPUs also not. And this is why in the high energy physics community has become so interested in quantum computing, because it really looks like a promising way to go for us. I think that was my last slide for particle physics, and now I promise I will stick to more quantum related stuff. So yeah, the main challenge that we have been tackling in my group in Maastricht, but also in many groups scattered internationally, I would say, is track reconstruction. So track reconstruction means you have charged particles leaving hits. Hits are just three-dimensional points. You have the coordinate of the hit in the detector, and that's all you have to reconstruct the tracks. You have to maximize efficiency, so you have to keep as many tracks as possible, real tracks as possible, and you have to minimize fake tracks, because events this enormous have so many possible combinations that if you think of it as a geometrical problem, you may as well build something that looks like a track, but is actually not a track. And these tracks are actually very dangerous for the physics measurements, so we have to keep the rate of those down. And then, well, the way we do it is building segments between the layers of the detectors. You would have one hit in one layer and one hit in the next layer, and you build that segment, and then you assess the compatibility of that segment with the segments afterwards. I put this just merely to emphasize how big the situation is. So this is one collision. It's not LHD, but it's one collision, and these are several primary vertices, and they are all the tracks. So it really is a problem that is very difficult to solve.
So you mean those are all possible solutions?
These are all the solutions, and the centers are the primary vertex is what we call the initial particle that led to the cascade of decays afterwards.
Only one is true.
Yeah, only one is true. Here there are no.
So you know where are the centers, where are going to be? That's something that when you do the experiment, you know?
No.
No?
No.
Okay.
We don't know. Now we know the region, but we don't know, and that's actually something that is also very interesting and something that we can do with track reconstruction. So when we try to approach these algorithms, classically and quantum, we can go two ways. The definition is not exactly black and white, but we usually call local tracking methods, where you have a series of steps. So this means first you go to the three first layers of your subdetector, then you extrapolate, so it's a sequential way of dealing with this problem. And there have been some studies on quantum computing, and I will show you one. But I'm going to focus more on the second part, which is global tracking methods. Global tracking methods mean all the hits are considered as one. You can actually think of this as a clustering sort of algorithms. And this, in my opinion, has several advantages as opposed to this one. First, you take all the hits at once. Once you have solved your problem, you have solved your problem. You don't have to go step by step. And second, because this is a clustering sort of problem, you can use many algorithms that are very well known to deal with this. So you have QAOA, you have quantum annealing, you can use Hopfield network, the half transform, and all the quantum versions of those, or even quantum native algorithms. QAOA is quantum native. But yeah, and then we talk about advantage basically in two terms here in high energy physics. We say a time speedup, but also an improvement in the complexity of the algorithm. And that's what we basically want to achieve. Either one or the other, or both, but yeah, both doesn't seem too feasible. So the approach we have mainly been working with in Maastricht is a QUBO formulation. So QUBO stands for quadratic unconstrained binary optimization. So you have all your hits, and you want to end up with a bunch of tracks. I mentioned to you that we will segments from these hits. So for us, a segment is a doublet of hits. So two hits in consecutive layers in the detector. So we can profit from the knowledge that we have on the detector geometry and how the track should behave to build a Hamiltonian that's a nicely like Hamiltonian. And then, of course, this is very, it's very good news because an IC like Hamiltonian, it's very well known. You have a bunch of things to find the ground state. So I show you here the expression. Now, a few remarks. Of course, this is not a fundamental formulation. You can add as many terms as you want if you have more input on what your track should look like. But you have to be a bit careful because if you constrain the solution too much, you end up in some sort of, it will only work for the simulation that you're using, but it will not work in the real world. If I take these angular terms, this angular term that's inspired from the Denby-Peterson model, if I take this alone, then I will end up with something that's too loose. And I actually tried this alone, and basically the algorithm told me, well, just put all the segments to 1 and you will have real tracks at the end, which is, of course, not what we want. So this is the Hamiltonian. It has 3 terms. This is the angular term. So these S's that you see here are the segments. These are binary values. This can also be a continuous variable, but for now, these are binary values. The segments are switched to 1 when they belong to a track, and they are switched to 0 when they don't belong to a track. So you have taken 2 hits from consecutive layers that actually don't belong to the same track. So the angular term that basically tells you try to get the segments to be as aligned as possible to each other because we are not considering curvature, so it should be a straight line. And then 2 penalty terms. The first penalty term is forbidding segments to share heads or tails. So you cannot have a track where you have this or this between 2 layers. And this is like a normalization term that keeps the number of segments more or less around the same number of hits. Because if this term is not there, as I told you before, it can happen that the algorithm says, okay, yes, all the segments are correct, and you have the solution in there. But this is something we want to avoid because of the clone rate. So we introduce this term. Now, these 2 parameters, alpha and beta, and well, actually lambda as well, they are not fixed. They have to be fixed once you try your quantum algorithm, but they are not fixed per se. And actually, this will vary a lot depending on your experiment. What I've been doing is trying simulated annealing to find the optimal value of these parameters. So I tried with the classical baseline, and I say, okay, I will plug in the values of alpha and beta that lead me to the solution faster.
Yeah. To understand. So what are the data? What are the variables?
So this is data. This is data. These are the variables. Any S is a variable. This is data because they are computed beforehand with the segments. And the Greek letter, well, lambda, alpha, and beta are fine-tuning parameters. Yeah.
RAB means
RAB.
2 points or 1 point. One.
RAB is the modulus of the segment AB. From the hit A to B, the modulus in 3D. So the Euclidean distance between the 2.
A and B.
Yeah, okay, maybe, okay.
You have seen something in A and something in B.
You have a hit in A and a hit in B. So you build a segment, and this segment will be called SAB.
Okay.
And the distance, if it's 3D, then it's called RAB. Now, theta ABC is because you have segment AB and segment BC, and this is the angle between the 2 segments.
If A and B are very far, you also include it between the all years.
Nearest neighbors. But for now, because I'm using just a toy simulation, when you add a very large amount of layers, the input will be also hard to deal with. So we may need to skip layers, and then this will be larger because you are taking closer neighbors. Or you also may say, okay, I don't want to ask, so far it's only nearest neighbors. I may also need to include more terms and make it cubic. That's also, it's nothing prevents this formulation from going there. Just that this is done as a, baseline study.
They're assuming that we have a 100% efficiency in all the detectors in this case.
Yes. I'm assuming 100% efficiency and straight tracks, and none of those are exactly true, of course. We are actually starting to try to assess multiple scattering and things like that. But for now, I will show you this is already enough of a challenge, so we decided to focus on that. And then,
the second question,
yeah.
That all the keys that you have in the data set belong to the same event.
Yes.
Which means that you have not mixes.
No. No, which could also happen in the detectors pileup, but for all of this we use simulation, so we have a lot of control over that. Okay. And even if we go all the way with this, we will only be able to use simulation and then try on data. So tractor construction for LHC experiments is built on simulation. The numbers, the efficiencies are computed from simulation and then are applied on data, and well, they are not recomputed again.
Okay. And finally,
yeah,
sorry.
Yeah, no, go ahead.
About these standards that you have.
Yes.
The
yeah.
Maybe because you are working a forward scattering, in this case, these samples are limited in number also.
Yeah.
Maybe because the geometry and the kind of events that you have.
Yeah, actually this term was a bit painful because the thing is, as I said, we actually took this, at first we took this lambda term from a paper that used simulation from CMS. So of course their case is completely different, they tracked them twice, and what happened is if you're not careful and the angles are very small, you may not see the variation well enough for what you want to do. So I'm trying with this, lambda I set to 1. I have a colleague that's trying with a step function, purely that, because the angles are very small already. And then one thing I haven't said here is that, well, I've been telling you a segment is 2 hits, but this is not what everybody is using. It can also be a triplet of hits, which come with disadvantages and advantages, but I will go into that later. But yeah. So you have this Hamiltonian. We started with gate-based quantum computers because we have a collaboration with IBM Research. So we have to take this Hamiltonian and rewrite it in terms of quantum gates. Actually, what comes out of this is that the quantum circuit that you will have is very deep because of all the possible segments that you can end up with. It's really deep, but it doesn't have complicated gates. I only have set and set gates. So it's deep, but it's somewhat trivial. And we had some discussion with IBM people. They were not too worried for now that this would be a problem. But then comes the algorithm, QAOA. So QAOA, I know this is a very well-known algorithm, but I'm going to go briefly through it. So it stands for Quantum Approximate Optimization Algorithm. It's an algorithm that's very beneficial to solve combinatorial optimization problems, such as the one that we have. So the way it works is you have your quantum state, and then you apply unitary operations that are of the form here. So you have 2 Hamiltonians. You have the problem Hamiltonian, which is, whereas this one that I've been showing you, this is the Hamiltonian for which you want to find the ground state. That's your solution. And then you have the mixing Hamiltonian. So the mixing Hamiltonian is there to make sure that you do find the ground state. If you don't put the mixing Hamiltonian, it will stay there and not go towards the minimum. So this algorithm is basically an approximation of the of quantum annealing, only gate-based, and it follows the adiabatic theorem. Now you can apply this a number of times. For different types of problems, you have to apply more times these unitary operations. But for now, I've only applied it once because my simulation was simple enough. But yeah, then you can see two things coming up. First, you have a mixing Hamiltonian, even if you take the simplest version of it, which is basically the one NISQ suggested, which is an X gate. You still have even more gates in your quantum circuit. This doesn't help the quantum volume. And also that you have these two terms, beta and gamma, because you prepare the quantum state, you compute the expectation value with your Hamiltonian. And then a classical optimizer tells you, okay, try with this new set of beta and gamma, and go through it again until you find a value here that's close to the minimum. So this is quantum, this is classical. And you need to find optimal values of beta and gamma, otherwise it's not going to converge to the minimum.
Beta and gamma should be different numbers.
Yeah.
That's not the same for
yes, yeah. So this is what I've been working with. You see the simulation here. It is the simplest case that one can find. I only consider 2 straight tracks, which are the things that you see in orange here, and 3 detector layers. So, this is the simplest use case you can think of. And still here, you have 8 possible segments. So you can only imagine how this scales to a realistic case. And 8 possible segments, I didn't use any embedding. Of course, I can use embedding and reduce my number of qubits. But take these 8 segments, and you end up with a circuit where you have 8 input qubits, where each input qubit has 8 numbers that can be 0 or 1 that correspond to each segment, and it will tell you, okay, this segment is off and this segment is on. So this histogram, I actually had to cut the label because it's like 256 possible combinations. So this is problematic, and this is something we are aware of. So you have to believe me when I say I found the correct solution. But of course, I found the correct solution for this case, for which I had fine-tuned my parameters for the penalty terms. But actually, it turned out that it's actually not so sensitive to the penalty, to the parameters of the penalty terms, but still, yes. No, this is very short, 1 minute. In simulation, 1 minute.
Why don't you get more statistics?
More shots. Yeah, I could have. I tried, but yeah.
Just to check that is the result.
Yeah, no, good point. I think I tried before, but this is the last one I tried. So yeah. But yeah, good point. So things we are working on at the moment. Well, now that this works, increasing the number of layers and the number of hits, and you have to add a curvature. Implement metrics, so the efficiency of the tracks, so how many real tracks is it able to reconstruct, and how many clones. That means, well, clones are, you have 2 candidates with this starting with the same hit. So yeah, this is something we are working on. We have been also working towards using actual LHC simulation, which is far more complex. And then, of course, the natural way to go would be, well, trying with quantum annealing. So we have some access to the waves from that network. And so we are trying to implement the Hamiltonian there and see how it behaves. So far, it behaves okay, but again, with the toy simulation, we don't have any, we have some preliminary results, but nothing that differs from our gate-based approach.
How would you do it?
quantum annealing is, because we use D-wave, we build the Hamiltonian, and basically we just need to call the function D-wave and specify which is the quadratic term and which is the linear term, and it finds it for you. It's like,
What do you mean at curvature?
because so far I've only been considering straight tracks,
Yeah.
which are the tracks at the very
Okay.
beginning, but they are actually curved. So in the angular term, I've been using that they are straight tracks, but it's not true for the rest of the data.
Then if you want straight tracks, you want to penalize the curve.
Yes.
Take lambda very large.
Yeah, you can take lambda very large, and you penalize long segments here with big angles. That's what this term is doing. But if you want to add curvature here, this does no longer hold, and you probably need to add another extra term. Or there's some ways to go around it. You can do a pre-processing of the tracks. You can focus on the mostly straight tracks until the very end, or you can add another term and deal with it.
And it wouldn't be in two combination.
No, it depends. I'm actually not sure if you add a curvature. I hope so. If it's cubo, it would be better. But yeah. Okay. Now, yeah. I've only been talking about LHCb. That's my personal bias, but there is actually a lot of related work on that. So, for example, there's this proposed experiment looks at DAISY that wants to study quantum electrodynamics using lasers. And in their case, what they will have are positrons traveling through 4 layers of tracking detectors. So they've also tried, and they published their results, which are quite interesting. They've also gone from the cubo formulation. So you will see that the dependency is essentially the same. Now there are two differences with them as compared to us. The first one is that they use triplets. They don't use doublets. Yeah, for us, we could use triplets, but then we would have to rewrite the Hamiltonian because the terms will change. It's not difficult to do, but you gain in the sense that you are tackling a problem that is harder from the classical point of view. But then the terms that your QAOA has to deal with are more complicated, and you have less control over them. So this is one thing, and this is the second thing is that they have this linear term, similarly to what I showed you before, but they actually say in their paper that this term they set it to 0. They just deal with the quadratic term because it seems to work better for them. And then they have 2 classical methods against which they benchmark this. First is a Kalman filter. It's basically the standard way of dealing with track reconstruction in particle physics and graph neural networks. So yeah, what they have tried is a variation on quantum eigensolver, which is hybrid quantum and classical. They went into some discussion because of course they bumped into the same problem as we do and everybody does, and that is the input. But even if you take triplets, you still have a large number of combinatorics and possible solutions. But what they did is to make subsets. They call it subcubo of subset of triplets that I'm considering and solving for my cubo, and then I go to the next one. And I show you here 2 of their plots with the efficiency and the fake rate, so the rate of fake traps. And this parameter that you see is the parameter they define in Lucio to distinguish the strong field regime that they want to achieve in this experiment. So basically this needs, the higher this is, the better. So we should be looking at these regions of the plot. Now you can see that the classical as compared to the quantum, which is the green one, is, yeah, of course, well, better because the efficiency for the green one to the quantum one is lower and fake rate is higher, but still it's pretty impressive and they still have good numbers because the efficiency here is 70%, is pretty good for a first approach, and then the fake rate is 0.2%, so it's not something crazy, you know, this looks promising. And yes.
So what do you have for these?
No, this is just an example of the variation in quantum eigenvalue.
Yeah,
So
but what are you calling in that circle?
the triplets.
What is that? So,
A triplet is 3 hits.
Three
3 hits.
hits.
Three hits.
It's a generalization of the seven.
Yes.
Uh-huh. What hits?
3 hits. So instead of taking 2 hits in 2 consecutive layers, they take 3.
So basically, there's a track that goes along the
Yeah, you
all the three.
Yes. You have tracks that go through all the layers. In this case, there are 4, and then you build the 3 hits,
Yeah.
and then you take another 3 hits
Yeah.
that overlap, and then you assess their compatibility to belong to the same track.
So these TIs that you were showing before, T 0, 1,
Yeah.
mean what?
These the TIs are binary values for the triplets. 0 means triplet belongs to trap, so the 3 hits belong to the same trap. Sorry, don't belong to the same trap. That's 0. They don't belong. 1 is they do belong to the same
So
trap.
the same as before.
Yeah, same as before, only triplets.
And BAJ is made out of data.
Yeah, similar as before. Here they use the geometry of their own detector, and here same for us, but the geometry of their own detector, and this actually they set to 0.
The BAJ have to insert the information of the hits that you got.
Yes.
You want to penalize something before.
Yeah,
You want to-
yeah.
Somewhere in the paper.
Yeah.
something-
I don't think the explicit expressions are there. They say that this is positive if they don't belong to the same trap, because this is the quantity to minimize, and negative if they belong to the same trap.
Whether they belong or they don't belong, you find out the heats.
Yeah, it's something you find out, but you use in simulation, so you have some information. You are implicitly feeding the information at the beginning, because we are also doing that by feeding it the angle they take.
So why is the strong field regime? So why is it different?
It doesn't matter. It only matters to interpret these plots because it means that you have to look more towards the right, because they want this quantity, which is where the strong field regime is accomplished, to be high. So it only matters in the sense that, well, they have tried different values because this is not a built experiment, but you should be looking at the numbers here, the last ones. But yeah, basically the approach is the same.
The problem looks very similar to the previous one.
It is
Why
exactly
don't you
the same
use
problem.
QAOA?
That's a matter of choice.
Ah,
It's a matter of choice. The usage of QAOA and of triplets is a matter of choice. From what we have discussed with the authors, if we arrive at the conclusion that, you know, the problems are the same, which is the input and how to retrieve the output. We are not at the stage yet where we can say which one is performing better, because we have bigger problems with the input and output. True, but I could also have used nonlinear time evolution. It's a matter of I use QAOA because it seems more built for this type of problems, and also because in my group there is more experience with that, and it's closer to quantum management. That's the reason. But
Depends on the number of layers that you have to make.
that is true. Yeah, that is true.
If you have 2 parameters per layer,
Yeah.
But the problem is you have to use the large number of layers.
Yeah.
In case it's
Yeah.
you have to add layers.
Yeah.
But you can just you have to add.
Yeah. So this is my personal opinion that at this stage of these research lines, it doesn't matter too much which algorithm we use. We still have the input and output problem.
Using this small number of input data, have you tried to use quantum phase estimation?
No, not directly. We have another person working on a different method for traffic construction that arrives to quantum phase estimation, but we have not used it directly. But yeah.
And you have to find the minimal value of the fact when you are working in variational quantitative solver, you are looking for the minimum error. It cannot be a different kernel, but the minimum error of the kernel is the minimum value of the kernel. So using quantum phase estimation, you can look for this minimum value that produces your solution.
Yeah, that's
Assuming
that's actually a good point. Yeah.
We're looking for the minimum value of one. So
Typically, you assume that you input the eigenvector and then you get the eigenvalue. That's how we do it. You get the eigenvector, the solution to the
Your problems are around. Your problems are all around. So you have to
Just for my understanding, this later formulation is maps to the previous one in the sense that the B coefficient and A coefficient know the information about the thetas are the okay.
Okay. So sorry.
How many layers were you using before in the first?
For me, 3. For me, 3 layers. Here, here they use 4.
And in this approach, what are they comparing in those plots?
Oh, right. Yeah. So the green one is the quantum, the hybrid quantum classical, so the new one. And then all the 3 other ones are the classical benchmarks. They are classical methods.
And the DQE with how many layers?
For all the layers, the same layers for classical and quantum field.
And how many parameters?
How many parameters? That I don't know. Because they were not very explicit about the expression. So I wanted to give a few words about local tracking methods, because so far I've been focusing on global tracking methods, and I put the reference I've studied for local tracking methods. So in this paper, they use the CMS tracking, just very much what the rest of experiments use for tracking. And this is a sequential tracking, and it has 4 steps that are depicted here. So classical. So the first step is called seeding, because you will seed. You will seeds or 3 hits in the three first detector layers that look like good candidates to start your reconstruction. Second step, track building, you extrapolate these 3 hits to the next layer. And well, you see here, you have some region of uncertainty because the detector is not perfect and the hits are not point-like. And you choose what is the best of these to belong to the same track. So you build tracks like this and you go through all the detectors, through all the layers sequentially. Then the third step is cleaning. Well, basically because you have so many possible combinations that it may happen that you end up with spurious tracks or hits that don't belong to any track, things like that. So cleaning based on the best track candidates. So the track that you end up with should give you the best efficiency, and selection of your final tracks. Again, so these two are mostly post-processing. You have built your tracks here, and here you get rid of double candidates and you select the candidates that are going to give you the best performance. In this paper, what they did, I will not go into much detail because I'm not really an expert on complexity theory, but I think it's an interesting read. And what they have done is go step by step, and they have assessed the complexity from the classical algorithm, so here, and the potential quantum speedup, or the improvement in the quantum complexity. And then they define its complexity in terms of the number of particles that you have, the number of hits, the number of seeds, and the number of candidates of the track. So, yeah. The takeaway message from this paper is they claim that you can gain something, especially in the first 2 steps, if you apply a variation of Grover's algorithm. Then you improve a bit the complexity. I think this is a conservative claim, but yeah. And then they also say that in the cleaning part and the selection part, there's not much to gain from the quantum point of view. As far as I know, the algorithms are sketched in this paper, but there's no actual implementation. As far as I know, if somebody knows the implementation, please send it to me because I'm very interested. But yeah, I mean, the message to me sounds a bit pessimistic because Grover's algorithm is not the thing that people are looking more in this case. But yeah, it's still a nice read in terms of complexity. It really helped me understand. Then, yeah, so I think I've already mentioned this a lot, but there are 3 main problems when you want to assess track reconstruction with quantum computing. First is scalability. The number of qubits that you have to input your circuit. It grows a lot. Like I have 8, and yeah, okay, IBM promises is 1,000, fine, but this is going to be very problematic. Second, the depth of your circuit to cope with the number of tracks. True that this is not as worrisome, but then you will also be more sensitive to noise, decoherence, all of that. So yeah, this is also something to care about. So these 2 are mostly input related, but then what do you do once you get your output? Because the way we have the algorithms, you end up with a string of zeros and ones that tells you which qubit is on and off, but they don't tell you to which track they belong. So you have to do some post-processing, and in doing so, you basically have to collapse the wave function, and you may lose your quantum advantage can be on. You have to do this, especially if you go to realistic case. There are some thoughts like, I think you can think of this as more like a building block. I have my algorithm here, it outputs this, and I hope in the future there will be something after this. So the pipeline of the high energy physics experiment will continue quantumly, and then I don't need to collapse the wave function. You can also go for the reducing the problem and saying, maybe I cannot get all the tracks, but maybe I can find the primary vertices or the angles of the tracks, the slopes, because then you have to collapse the wave function less and you can reduce the problem of it. But it's still a problem. So it's really highly non-trivial to do this. In all the results that are published and that we are working on, we always do this post-processing, which is not quantum. Then, yeah, I don't know how I'm doing time. Oh, okay. So, yeah, I will talk a bit about the other projects that we have in Maastricht. One is flavor tagging. Flavor tagging is in an experiment like LHCb, you start with a quark that you want to study, and you need to know the flavor of this quark. But because it's such a messy process, you don't know it a priori. But you can infer it from the decay products. So it's a classification matter of distinguishing the flavor of the quark, if it's P or anti-P. And this is actually the first paper that was published from an LHC experiment on quantum computing, where they use quantum machine learning to try and understand the flavor of these quarks that were produced, that led, so you have the quark and then you have a jet. And you have variables associated to the jet that were used for the machine learning classifier. And the results were compared here. There are two colors because different embeddings. And again, take this with a pinch of salt. Yes, it's quantum simulation, and it's still worse than the classical, but it's still pretty good for what we use, for the numbers we deal with at LHCb. And this is something that we have been pursuing further. So we have tried different architectures. We have started implementation in hardware. Actually, implementing it in hardware yielded pretty good results. We were more scared about noise that we should have. But anyhow, it's worth looking into this. And then we have students looking into noise mitigation techniques, noise correction techniques. This is nothing new. We are using the tools that IBM provides, but we are looking into how to improve these numbers in hardware. Yeah, I think this is my last slide. So there are a lot of topics I didn't cover. There are actually a lot of ideas from DESY, QTI, USA, a lot of people. There's theory with lattice QCD. There's quantum anomaly detection, which is basically quantum machine learning to take the data straight from the detector and identify anomalous events. That can mean anything for particle physics. There's detector simulation, which is also quite interesting for our studies. There's even quantum computing for beam steering. So the steering of the beam, the alignment of the beam and the detector, which I find really interesting, but I don't know how this is going to work because this really should be exactly at real time. But yeah, and these are my conclusions. So quantum computing, it really has great potential with the most difficult challenges that we have in high energy physics. But we need to be a bit careful and really, we have the same bottlenecks as the community does, and we have to deal with a large data, and we have to think about this. But still, there are some progress made and some cool results that can be an initial point to further development and more realistic cases. Yeah.
So we have some time for a few questions if you want to ask. If anyone in Zoom want to ask something.
I have problem to visualize the quantum qubits. You need as many qubits as layers.
Yeah.
And as many plus qubits for hits or not.
Yeah.
Or hits only.
I think this is better if I write it down.
You can write in.
Oh wow!
Yeah.
Very fancy. Okay.
Yeah, and you have the pencil there.
Okay, so this.
No, there is a pencil below the
Okay.
You can also use the finger. That is what it-
No, yeah, okay. So, yeah, say for example, you have one layer only, and then you have this. You have 8 qubits. So the problem Hamiltonian, you can decompose in something set gate, something set gates, say this.
Yeah.
Then this is the,
But
Yeah.
my question is about well, you have 3 detectors.
Yeah.
And 8 particles with
Yeah.
each first
Yeah.
hits per detector.
Yeah.
How many qubits do you need?
8. No,
Eight,
but at most 8. You can do embedding
Okay.
and
So-
reduce it in half.
Okay. As many qubits as hits. Layers are
As many qubits as combinatorial as combinatorics. I think this scales like it's
You have to close the events of-
yeah.
Yeah.
okay. This is 8 because it's 2 to the power of 3.
Okay.
So it scales like that.
Okay.
The layers of the quantum circuit will depend on the how complex your Hamiltonian expression
Yeah,
is and
yeah.
the qubits.
I mean
Yeah.
layers as
Yeah,
detectors.
Yeah.
Just to make it clear, is the number of hits in total in all of the layers of the experiment. Is the number of qubits you need. So you need 1 qubit for each. In the case, okay. Okay.
No, it's you need 1 qubit for possible solution of this overall solution.
Sorry. Okay, so it's combinatory. Okay.
Yeah, it's combinatory.
Okay. Understood.
So what do you know the number of solutions? You're punching all the points into the bracket.
Yeah.
The number of matches.
The number of tracks you know from simulation, and you enforce it here.
The number of segments that are two.
Yeah. No, I think this is the number of
Yeah,
hits,
so-
not the number of tracks. But
The
yeah,
total number of segments.
no,
In a
no, es un qubit por cada solución de todo esto.
Porque hay 8 soluciones.
Sí.
Ah.
Sí.
In a typical experiment,
Yeah.
realistic experiment, how much layers do you have? How many? Because you got like
Yeah.
40 million.
Yes, in
hits.
the yeah. So just in this part, the velo where I told you we were focusing on because it's straight tracks, 52 layers.
Okay. Layers. And,
Yes,
how many hits do you expect generally?
that's
Ah,
all. 1,000
Oh.
in a regular event. 1,000. So,
1,000 to the 52. Okay.
yeah, scary.
That's a large number. Yeah.
Yes, no, you can clean up. You can say
That's why you try to do this on the fly, let's say.
Yeah.
Like do the same calculation lots of times per second because
Yeah.
if it accumulates, it fills your bandwidth.
Yeah. Yeah.
And
Mhm.
And then something that was brought up that is true is that the angle that goes into the Hamiltonian, you have to compute it. That's also a classical operation you have to do,
Mm.
which is true or not true, because if it comes to that, you can get it from it. It doesn't need to start in your time. It doesn't need to count for the time you spend. But it's still you need to do.
At the end, you get the angles between people.
Yeah,
It's
exactly,
only once that you
pre-computed.
get the angles.
True. It's only once, but do you want to count? If you count them here, you are screwed.
Yeah, but the problem is that we have some restrictions from the angles that we have.
Yeah.
We have one track from one area to another, and
Yeah.
an angle of almost 90 degrees.
Yeah, no, that is true. And also in classical reconstruction, they also use variables. So we could do the same. It's not,
My question is, so why is it so important to reconstruct all the tracks? I mean, what is the question you want to answer? Because
okay, it's important
we
that,
want to find where the vertex is.
no,
We are overthinking the problem.
the tracks are important at the basics of the experiment because from the reconstructed tracks comes every kinematic variable that you will use. Every kinematic variable. And then it has an extra complication because it's not only the tracks that behave well that you care about, it's actually the weird tracks that you want. It's the track, the weird tracks, the tracks that
Yeah.
curve more or curve less. Like say, imagine you want to find a particle with charge 2, which
Maybe
was
why
that?
don't we focus on those ones?
Yeah,
Instead of representing all of it. You penalize everything which is kind of trivial.
yeah, that's the
which
way
you
to
are not
go.
interested, and understand something.
Yeah, it's a way to go. If you want to reduce the problem, yeah, it will come to that. No, it will.
That you're over. Doing that, like,
No, because that's also what the classical is doing. You need a lot of flies. It's a big problem because you need all of them. It's really not to work around, and because it's at such an early state of the data taking that you cannot afford to lose a lot of things that you need.
That regard after trigger, maybe after some specific trigger.
This
Because that will reduce a lot.
Yeah,
of
yeah,
number.
we tried after trigger. She suggested. Yes, it is. Yeah. I mean, real time for this is a bit like, okay, maybe not 2050, maybe 2100. We will try. But yeah, after trigger, yes.
If you are looking on the figure, in the process of not the discussion, not doing, you just have ways of evidence per second that is correct.
Yeah.
And you are looking at the solution using optimization that is ability to see more problem. So I wondered if really this kind of solution would work at this point. Because first of all, you have many concerns about how many steps in the solution have to be. That will increase the number of parameters, and you are working with thousands of inputs. So really, this happened the last slide to do so the scalability of the method.
Yeah.
But the most important part is not really the scalability, it's the timing of the method. Okay. And if you have an NISQ, it's completely unknown the number of steps that you have to do.
Yeah, that is true. That is very true. Now, there is another line which is trying to approach it like a system of linear equations. But that comes with a whole bunch of other problems. But at least now the steps are defined. So it's always like that. Different algorithms, you will bump into different roadblocks. But I'm not, from my point of view, I'm not that set on QA. Like I do think when it comes to actual implementation of realistic cases, we will need to have another look at the algorithm.
But in fact, I feel that you need some algorithm like the soft algorithm. That
Sure.
every measurement that you have is a candidate for the answer.
Yeah.
With a very few sorts, you can make a decision about the event must be described for the moment.
Yeah.
if not, we are working with something that is particularly in
Yeah, but then that also depends on the practicalities, right? Because the good thing about QA is that it's okay for the NISQ area, and on the short, yes, but long term. For me, I think as long as you approach this problem as a building block, yes, makes sense.
I have a small question about the component.
Yes.
The first 5 minutes, I think that is enough. That is related with the efficiency of the detector. Okay. If you want to improve the efficiency of the detector, which means that you have to modify this.
Yeah.
It's convenient to put some components that actually work.
Yeah.
And you have to include the possibility that some zero that we have.
Yeah.
It's not really a zero.
Yeah.
We have a
Yeah. Yeah.
something that we call
Yeah.
because it's not
there. Yeah, exactly.
Have to explore these possibilities of first of all, I don't know the efficiency of the detectors. I don't know if they are close to 100%.
Yeah, I think it's
not.
they always quote a very good number, so I think I have the here. Yeah, it doesn't say how they say it's very good, so you will have to believe me that it's very good, but they don't say the number.
Okay, you can generate the efficiency so not higher than
Yeah. Yes.
What happens if the detectors are less efficient? The points you see are sparser. There are many detectors that didn't I mean, where there's a hit that didn't show. So it becomes sparser. But on the overall, what is telling this Hamiltonian is that if the distance, so it will penalize all the tracks in the same way. You want to have 2 points to belong to the same segment, and you penalize the ones that are very far because it's divided. The distance is divided.
Yeah.
The ones that are very far, but it's penalizing the same.
but imagine that you have a detector with a battery. Okay, you have one segment from here to this one. What's happened?
No. I was supposed that the efficient was.
No, but
It's not.
Javier made a very good point there, because it's true that this you can bring it down to multiple scattering in the layers of the detector. So it has some fundamentality to it. Now, it's true that if you want to derive this term from multiple scattering, you're also accepting that this is not a perfect detector. But at first order, it should mean that this is not, you cannot make Kronecker delta. And you cannot constrain this so much.
In fact, the problem here maybe is easier than in the next one. In the next one, we are working with the next.
Yeah. Yeah, exactly.
Assuming that you can
That exactly. That's the problem that comes up with triplets. But our ideas to introduce the inefficiencies would be that compute this with multiple scattering, letting the terms a bit looser and see how they behave. And then if we could, there's the stochastic noise of the detector that you cannot parameterize and it cannot be inserted into the Hamiltonian, but maybe there's a component that could, because at the end, the noise also comes from detectors which are made of elements, so you could try that.
And my last question. Regarding the scalability, the classes like that.
Yeah. Yes.
You know, if there is not the other one.
Oh, this one. Yeah.
Yeah. I'm thinking about the first problem that was we have to process the information, and maybe we have one deadline for deciding if we want to store or not there. I don't know if it's 1 second, I mean, doesn't get from this. You know, if someone had to study the velocity of the imagine that we have, which is scalability. In the number of arm operation. The race or the issue that we should have in the quantum computer in order to achieve these requirements of the deadline for the signing
Mhm. The time,
the time.
yeah,
Escality, the time.
no, I'm not aware of that, but I don't know how the coherence time for current quantum computers are.
No, depending on the problem is that it's related to the speed of the operation, because if you're using ion traps, for example, in this case, you have a very long, no, you can do longer times. You want around, you can maybe achieve 1 second or 2 seconds.
Yeah.
But the problem is that the pressure side, I probably used to be 1 millisecond for the last model.
Yeah.
If you go to superconducting qubits, in this case, the time more or less you can think in the next years around 200 microseconds.
Yeah,
But in this case, you have nanoseconds.
yeah,
That's not the measurements that you do.
Yeah.
So my concern is not related to the scalability.
yes,
It's the
Yeah.
scalability of online.
Yeah.
Because of course, the classical computer will have bigger.
Yeah.
The quantum computer is not clear that it can go to.
Yeah.
this space that is
yeah, no, yeah, that's definitely a legitimate concern. I worry about that too. But yeah, that I'm not sure how to work around that. One is, I mean, well, not for this, but for the global methods, annealers. For these, divide the problem, maybe try maybe some error correction instead of error mitigation. But yeah, I'm not sure, because of course the bigger the input, the more problems you have with connectivity of qubits. So yeah, I'm curious to see how this is implemented.
I have a question. Again, the QAOA.
Okay,
Why did you choose that experiment with that quantity of qubits?
so this was the simplest case I could think of. Well, it's actually the easiest, because you cannot have one fact only. And then this yielded 8 qubits if you don't do embedding. That's why I had 8. Because if I do embedding, I reduce it to 4, but writing this Hamilton in terms of gates, it's already complicated enough when all the qubits are what they are supposed to be, let alone when you put some information in the amplitudes. So it seemed to me like the most straightforward way. That's why I put it.
Thinking about scaling the problem.
Scaling the problem, yes. And scaling the problem, I will have to refine my gates and my quantum circuit.
Because all the qubits are connected, or no?
And I've only been using some, so I don't worry about that for now. But once it comes to that, yes, that also matters a lot. So I will have to see how to do that.
Okay, well, just say thank you to Miriam. Thank you very much. Thank you everyone for joining. So see you next time.